The night of February 24, 1944, Anzio beachhead, Italy. 12 Luftwaffe bombers approached the confined Allied position under cover of darkness, confident in their new electronic countermeasures. German crews had been briefed that their Kettenhund radar jammers would blind American anti-aircraft defenses, just as they had neutralized the older SCR-268 systems. What happened next would fundamentally alter their understanding of American radar capability. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within seconds of entering the airspace above the beachhead, 7 of the 12 bombers were destroyed by precision 90mm anti-aircraft fire. The guns tracked them through complete darkness with mechanical accuracy that defied every assumption German intelligence had made about Allied radar. The Kettenhund jammers, effective against the 205-megahertz SCR-268 radar, were completely useless against something the Germans had not anticipated. 2 SCR-584 radar systems had been rushed to Anzio just days earlier. The German air attacks stopped for a week. This is their documented story, based on technical specifications, combat records, and verified historical accounts. The transformation of anti-aircraft warfare that German forces witnessed at Anzio represented more than tactical surprise. It revealed a technological gap that would influence every major battle from that moment forward. The Germans had built their electronic warfare doctrine around defeating radar systems they understood. What they encountered was something entirely different. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The SCR-584 emerged from a collaboration that began in September 1940. A British delegation, known to history as the Tizard mission, travelled to the United States carrying Britain's most closely guarded military secret. Among the technologies they revealed was the cavity magnetron, a device capable of generating microwave radar signals at 10 centimeters wavelength. This single component changed the fundamental equation of radar warfare. Prior to the cavity magnetron, radar systems operated at much longer wavelengths. The American SCR-268 radar, deployed since 1937, operated at roughly 60 centimeters. The German Würzburg, considered among the most sophisticated radars of its time, operated at 53 centimeters. These longer wavelengths limited accuracy and made the systems vulnerable to relatively simple jamming techniques. The cavity magnetron enabled operation at 10 centimeters. This shorter wavelength provided several revolutionary capabilities. First, the radar beam could be much narrower, dramatically improving angular accuracy. Second, the system could detect smaller targets at greater range. Third, and perhaps most importantly, existing German electronic warfare equipment was designed to counter longer wavelength systems and proved completely ineffective against microwave frequencies. At the Massachusetts Institute of Technology, the radiation laboratory was established in December 1940 specifically to exploit the cavity magnetron's potential. Under the direction of Lee Dubridge, with Alfred Lee Loomis running the division responsible for fire control systems, a team of physicists and engineers began developing what would become the SCR-584. The design specifications were ambitious. The system needed to automatically detect, track, and direct fire control solutions for high-speed aircraft moving at 600 miles per hour or faster. It needed to function in a combat environment with minimal operator intervention. It needed to be mobile enough to deploy close to frontline positions. The team developed several innovations that together created a system far beyond anything fielded by any nation. The conical scanning system continuously rotated a slightly offset radar beam around the antenna's central axis. When the target was off-center, the signal strength varied in a predictable pattern. Electronic circuits analyzed this variation and automatically adjusted the antenna's position to keep the target centered. The Germans had introduced conical scanning in their Würzburg radar in 1941, but the SCR-584 implemented the concept with far greater sophistication. The automatic tracking system represented the most significant advance. Once an operator designated a target, Servo motors mounted in the antenna's base kept the radar locked on without further human intervention. This automation reduced the crew requirements and eliminated human tracking errors that plagued earlier systems. The Germans required multiple operators, maintaining constant attention to track a single target with their Würzburg. The SCR-584 could lock onto a target and track it automatically, while the crew focused on identifying additional threats. The system specifications demonstrated its advanced capabilities. The SCR-584 operated at frequencies between 2,700 and 2,800 MHz, sending out 300 kilowatt pulses with a duration of 0.8 of a microsecond. The pulse repetition frequency was 1,707 pulses per second. These technical parameters enabled the system to detect bomber-sized targets at approximately 40 miles range and automatically track them at 18 miles with exceptional precision. The accuracy within tracking range was remarkable for the era. The system achieved range accuracy of 25 yards and angular accuracy of 0.06 degrees. This precision meant that firing solutions calculated by the associated M9 gun director could place shells directly in the path of attacking aircraft with unprecedented reliability. The Germans had nothing comparable in their arsenal. The physical system fit entirely within a single trailer, making it mobile enough to deploy forward with advancing forces. The 6-foot parabolic antenna dish, perforated with 6,640 half-inch holes to reduce wind resistance while saving 70 pounds of steel per unit, could withstand winds up to 60 miles per hour and survive hurricane-force winds of 100 miles per hour. This durability proved essential in combat conditions where equipment faced both enemy action and environmental extremes. Production of the SCR-584 involved American industrial capacity at its wartime peak. The General Electric Company, Westinghouse Electric and Manufacturing Company, and Chrysler Corporation spent only 11 months transitioning from the XT-1 prototype to initial production. By the time production concluded, more than 2,098 units had been manufactured. The Dodge division of Chrysler delivered system number 1,470 on January 28, 1944, just weeks before the first systems reached Anzio. The system's development had not been without challenges. The radar was intended for introduction in late 1943, but various bureaucratic obstacles and technical refinements delayed deployment to frontline units until early 1944. This delay, while frustrating to the development team, ensured that the systems reaching combat troops were thoroughly tested and reliable. The first operational unit was delivered in May 1943, spending the subsequent months in training units before deployment to combat zones. The M9 gun director, developed by Bell Telephone Laboratories, formed the second half of the weapon system. This analog computer received range, azimuth, and elevation data directly from the SCR-584 through electrical connections. The M9 calculated firing solutions accounting for aircraft speed, altitude, and direction, then automatically positioned up to 4 90mm M1 anti-aircraft guns. The gun crew's primary responsibility became keeping the guns loaded and firing. The entire engagement process, from target acquisition to shell trajectory calculation, occurred without manual gun laying. The system demonstrated its capabilities during testing in May 1941. Engineers mounted the radar outputs to a gun turret from a Boeing B-29 bomber, replacing the guns with a camera. A pilot flew his light plane around the test area while the camera recorded the system's tracking. On May 31st, the system accurately tracked the aircraft throughout its flight. This successful demonstration led to a contract for over 1,200 systems the following day. German radar development had followed a different path. Their Würzburg radar, first deployed in 1940, represented sophisticated engineering within the constraints of available technology. The basic Würzburg had a maximum range of about 29 kilometers and was accurate to approximately 25 meters in range. The Würzburg D model, introduced in 1941 with conical scanning, improved accuracy to around 0.2 degrees in azimuth and 0.3 degrees in elevation. This represented excellent performance for its wavelength and the technology available to German engineers. To further improve performance, the Germans developed the Würzburg-Riese, or Giant Würzburg. This system used a much larger 7.4-meter antenna and more powerful transmitter, extending range to 70 kilometers. Angular accuracy improved to 0.1 to 0.2 degrees, sufficient for direct gun laying. However, the larger system sacrificed mobility. The Würzburg-Riese was too large for road transport and was adapted for operation from railway carriages. Over 1,500 of these railway-mounted systems were produced during the war. The Freya radar complemented the Würzburg systems in German air defense. Operating at 1.2-meter wavelength, the Freya provided early warning capabilities with detection range up to 160 kilometers. The system was fully steerable and semi-mobile, but could not accurately determine altitude. German doctrine typically used Freya radars to detect approaching aircraft at long range, then handed them over to Würzburg radars for precise tracking and gun direction. This integrated approach represented sound tactical thinking, given the technology available to Germany. The problem was that German electronic warfare capabilities evolved specifically to counter these longer wavelength systems. When the British introduced window chaff and carpet white noise jammers, they targeted the frequencies used by German radar. The Germans responded with modified Würzburg systems, incorporating various anti-jamming measures, extending the frequency band to cover more than 100 megahertz. German intelligence was aware that the Allies possessed advanced radar capabilities. Operation Biting in February 1942 saw British paratroopers capture components of an operational Würzburg system on the French coast. This raid provided the British with detailed knowledge of German radar that informed their jamming efforts. The Germans similarly understood that Allied radar technology was advancing, but lacked complete intelligence on specific American systems entering service. The Kettenhund jammer represented Germany's response to Allied anti-aircraft radar. Specifically designed to counter the SCR-268 radar operating at 205 MHz, the Kettenhund proved effective when properly employed. German bombers equipped with these jammers could operate with significantly reduced losses against positions defended by SCR-268 systems. This success created confidence in German electronic warfare capabilities. The SCR-268 radar had indeed been America's primary anti-aircraft system since the late 1930s. Operating at roughly 60 centimeter wavelength, it provided adequate performance for its era, but was fundamentally limited by its long wavelength. The system required optical confirmation for final gun laying and was vulnerable to the jamming techniques the Germans had developed. By late 1943, the SCR-268's limitations were well understood within the US Army, driving the urgent need for the SCR-584's deployment. What German intelligence failed to appreciate was the magnitude of the technological leap represented by the SCR-584. This was not simply an improved version of existing American radar. The move to 10 centimeter microwave frequency represented a qualitative change in capability. The automatic tracking, the precision, the resistance to existing jamming techniques, all combined to create a system that fundamentally altered the tactical equation of air defense. The deployment to Anzio occurred under circumstances that highlighted both the system's importance and the desperate tactical situation. Operation Shingle, the Allied amphibious landing at Anzio, took place on January 22, 1944. The initial landings achieved complete tactical surprise with minimal casualties. However, the German reaction was swift and effective. Within hours, Field Marshal Albert Kesselring had activated contingency plans and began moving divisions toward the beachhead. By January 25, elements of 5 German divisions, approximately 40,000 troops, had surrounded the Allied position. The confined beachhead, measuring only 18 miles long by 9 miles deep, provided no room for maneuver. Every position was within range of German artillery. The flat marshland offered minimal cover. Ships offshore faced persistent air and artillery attack. The Luftwaffe, recognizing the opportunity to inflict significant damage on concentrated Allied forces, mounted intensive air attacks. The Germans assumed their Kettenhund jammers would neutralize American anti-aircraft radar, as they had done elsewhere. Previous raids had demonstrated the jammers' effectiveness against SCR-268 systems. Luftwaffe crews approached Anzio, confident that electronic warfare would provide protection from radar-directed fire. The older American radar systems at the beachhead initially performed as German intelligence predicted. The Kettenhund jammers successfully disrupted their operation. Then the first two SCR-584 systems arrived. Military records indicate they were rushed to Anzio and were emplaced and operational by February 24th. The systems were literally dug into defensive positions up to their trailer rooftops overnight, providing protection from counter-battery fire while maintaining operational capability. The radar antennas protruded above ground level, their 6-foot dishes scanning the night sky at 4 revolutions per minute in helical search mode. The evening of February 24th began typically for the German bomber crews. They conducted their pre-flight briefings, reviewed the known Allied anti-aircraft positions, activated their Kettenhund jammers, and took off for another attack on the beachhead. What they could not know was that the electronic warfare landscape had fundamentally changed. The Kettenhund jammers, designed to counter 205 MHz transmissions, had no effect on the 2,800 MHz microwave signals from the SCR-584. The SCR-584 operators detected the approaching formation at maximum range. The radar's helical scan mode presented the aircraft as distinct returns on the plan position indicator display. When the formation reached approximately 18 miles range, operators designated individual aircraft for tracking. The servo motors engaged, automatically keeping the antennas locked on their assigned targets. Range, azimuth, and elevation data flowed continuously to the M9 gun directors. The 90mm guns received their firing solutions and traversed automatically to the calculated positions. The gun crews loaded shells fitted with the new proximity phases, another technological development the Germans had not anticipated. When the Luftwaffe bombers entered effective range, the guns opened fire. The proximity fuses detonated the shells when they came within lethal distance of their targets, eliminating the need for precise altitude settings. From the German crew's perspective, the engagement was inexplicable. Their jammers showed no indication that Allied radar was tracking them, yet the anti-aircraft fire displayed accuracy that should have been impossible without radar direction. Aircraft were hit on the first salvos. The defensive formation broke apart as bombers took evasive action, but the SCR-584 systems maintained their locks, automatically compensating for the aircraft's maneuvers. Of the 12 bombers in the formation, 7 were destroyed before they could drop their ordnance on the beachhead. The surviving 5 aircraft broke off and returned to base. Luftwaffe intelligence officers debriefed the crews, trying to understand what had happened. The pilots reported accurate radar-directed fire, despite operating their jammers at full power. Something new had entered the battlefield equation. The German air attacks on Anzio stopped for a week. Luftwaffe commanders recognized that their electronic warfare tactics had been rendered obsolete. Eventually, a single reconnaissance aircraft was sent to test the defenses. The SCR-584 tracked it, the 90mm guns engaged, and the aircraft was destroyed. Within days, 10 additional SCR-584 systems were deployed to the Anzio beachhead. The Luftwaffe's air campaign against the Allied position effectively ended. The tactical impact was immediate and decisive. German air attacks, which had been a constant threat to Allied positions and shipping offshore, became rare. Ships could remain closer to shore, providing more effective naval gunfire support. Supply operations continued without the constant interruption of air raids. The confined beachhead, which could have become a death trap under sustained air attack, remained viable as a launching point for the eventual breakout toward Rome. German intelligence began piecing together information about this new American radar system. Signals intelligence detected the microwave transmissions and identified their frequency range. Captured equipment and interviews with captured Allied personnel provided additional details. What emerged was recognition that the Americans had deployed a radar system significantly more advanced than German intelligence had predicted. The technical specifications, once understood, revealed the magnitude of the challenge. The 10-centimeter wavelength meant that existing German jamming equipment was ineffective. Developing new jammers to counter microwave radar required different electronic components and design approaches. The automatic tracking capability meant the system was less dependent on operator skill and could maintain locks through evasive maneuvers. The integration with automatic gun direction eliminated the time delays inherent in manual systems. The broader implications extended beyond tactical air defense. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The SCR-584's ability to track fast-moving aircraft meant it could potentially track other high-speed targets. Military records document that the system was successfully used to track artillery shell trajectories in flight, allowing American forces to calculate the location of German artillery batteries from the shell's flight paths. This counter-battery capability provided another tactical advantage that German forces had not anticipated. The system's accuracy proved sufficient to detect and track ground vehicles at substantial distances. One SCR-584 reportedly detected German vehicles at a range of 26 kilometers, well beyond the capability of previous radar systems. This detection range gave Allied forces advanced warning of German armored movements, degrading the effectiveness of surprise attacks. After D-Day on June 6, 1944, SCR-584 systems were deployed with the invasion forces. 39 systems participated in the Normandy landings, providing air defense for the vulnerable beachhead. The systems had been waterproofed by Lee Davenport's team, specifically for amphibious operations. Once ashore, they provided the air defense umbrella that allowed the buildup of forces necessary for the breakout from the beaches. The radar proved easier to use in the field than the less advanced Canadian and British Good Luck Mark III radar. American crews required less training to achieve operational proficiency. Maintenance was more straightforward despite the system's sophistication. The single-trailer design meant that setup time was minimal compared to systems requiring multiple vehicles and extensive cabling. These operational advantages translated directly into tactical flexibility. The British rushed SCR-584 systems to England, specifically to counter the V-1 flying bombs. Starting in June 1944, the Germans launched thousands of these cruise missiles at London, from sites in occupied France. The V-1's speed of approximately 400 miles per hour made it a challenging target for conventional anti-aircraft systems. The SCR-584, with its ability to track aircraft moving up to 600 miles per hour, could maintain locks on the Vosne second throughout their flight. The effectiveness of the SCR-584 against the V-1 demonstrated the system's advanced capabilities. In the first week after the guns reached their free-firing positions on the southeastern coast of England, 17% of all flying bombs entering the coastal gun belt were destroyed. This rate climbed rapidly as crews gained experience. By August 23, 60% of Vosne second were being destroyed. By the last week of August, 74% were shot down. On one extraordinary day, 82% of the incoming Vosne second were destroyed before reaching their targets. The ammunition expenditure figures reveal the precision of radar-directed fire. Initially, one V-1 was destroyed for every 2,500 shells fired. This improved to one V-1 destroyed for every 100 shells fired. This tenfold improvement in efficiency reduced ammunition consumption while increasing effectiveness, a combination that demonstrated the value of precision fire control. The German response to the SCR-584 evolved slowly. Developing effective countermeasures required understanding the system's operating principles and creating new electronic warfare equipment. Germany's increasingly strained industrial capacity made rapid development and deployment of new systems difficult. By the time modified jamming equipment entered service, the tactical situation had shifted dramatically against Germany. The Battle of the Bulge in December 1944 showcased the SCR-584's versatility under challenging conditions. During the German offensive through the Ardennes, terrible weather conditions grounded most Allied aircraft. The SCR-584 systems deployed with American forces provided one of the few means of directing tactical air support. The radar's ability to track friendly aircraft through clouds and guide them to ground targets provided close air support that helped contain the German breakthrough. The system's ability to detect and track German V-2 ballistic missiles provided intelligence on the launch sites and impact points. One SCR-584 at Steenbergen detected 88 V-2 launches and successfully tracked 81% of them. While the tracking range and time were insufficient to provide useful interception data, the information gathered on impact points allowed Allied forces to direct counterattacks against the launch sites. German technical intelligence eventually acquired detailed information about the SCR-584 through various means. Morton Sobel, an American engineer, stole plans for the radar and provided them to Soviet intelligence. This espionage would have long-term implications beyond World War II. Soviet radar development incorporated elements of the SCR-584 design, producing systems that would later be used against American forces in Korea and Vietnam. The Soviet SON-9, SON-30, and SON-50 radars were all derivatives of this American system. The psychological impact on German forces extended beyond the immediate tactical defeats. Luftwaffe crews who had operated confidently with their electronic countermeasures now faced the reality that their protection had vanished. The confidence that came from believing they could blind Allied radar had sustained morale through increasingly dangerous missions. That confidence evaporated at Anzio and was never fully restored. German air operations against Allied positions became increasingly cautious after encounters with the SCR-584. Mission planning had to account for the possibility of encountering the new radar systems. Flight paths were altered to avoid known or suspected SCR-584 positions. Attack formations changed to reduce vulnerability to precision anti-aircraft fire. These tactical adjustments, while necessary for survival, reduced the effectiveness of German air operations. The strategic implications were equally significant. Germany's radar development program had produced sophisticated systems like the Würzburg and Freya, but these operated at longer wavelengths. The German decision to focus on decimeter and meter wavelength systems reflected both technical limitations and strategic choices about resource allocation. The British and American commitment to microwave radar, enabled by the cavity magnetron, created a technological advantage that Germany could not overcome in the time available. German industry in 1944 faced multiple constraints that prevented rapid development of countermeasures. Allied bombing had disrupted production facilities and supply chains. Critical materials were increasingly scarce. Skilled engineers and technicians were spread across numerous competing projects. The decision-making process for allocating resources to new radar development competed with demands for fighter aircraft, tanks, rockets, and other weapons systems deemed more immediately essential to Germany's defensive war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical challenge of countering the SCR-584 was substantial, even with adequate resources. Developing effective jamming equipment for microwave frequencies required different components than those used in existing German electronic warfare systems. The shorter wavelength meant that antenna designs needed to be completely different. The power requirements for effective jamming at these frequencies exceeded what existing German airborne systems could generate. Creating a comprehensive solution would have required months or years of development effort. By the time German engineers understood the technical requirements for countering the SCR-584, the tactical situation had deteriorated to the point where such countermeasures would have limited impact. The Allied advance after D-Day compressed the timeline for developing and deploying new systems. Germany's industrial capacity was being systematically destroyed by strategic bombing. The resources available for radar development could not match the scale of American and British programs. The SCR-584's success at Anzio established a pattern that repeated throughout the remainder of the war in Europe. Wherever the systems were deployed, German air operations became significantly more dangerous. The systems were used extensively during the advance through France after the Normandy breakout. They protected river crossings, supply depots, and forward airfields. They directed fire against German aircraft attempting to disrupt Allied operations. The operational flexibility of the SCR-584 proved particularly valuable during fluid combat situations. The single-trailer design meant that systems could be moved quickly to respond to changing tactical needs. Setup time was measured in hours rather than days. Crews could emplace a system, connect it to gun batteries and power supplies, and begin operations with minimal preparation. This responsiveness gave Allied commanders a tactical tool that could adapt to evolving situations. The integration with proximity-fused ammunition created a weapon system greater than the sum of its parts. The radar provided precise targeting data. The M9 gun director calculated firing solutions accounting for target movement. The proximity fuzzes eliminated the need for precise altitude settings, detonating shells automatically when they came within lethal range of their targets. This combination achieved kill rates that manual anti-aircraft systems could never match. The data from British operations against V-1 flying bombs provided quantifiable evidence of the system's effectiveness. The improvement from 17% interception rate to 74% over the course of 3 months demonstrated both the system's capability and the value of crew experience. The reduction in ammunition expenditure from 1 destroyed per 2,500 shells to 1 per 100 shells proved that precision targeting was economically efficient as well as tactically effective. German V-1 operations continued despite the high attrition rates, but the strategic impact was greatly reduced. Of the thousands of Vohn-2 launched, less than 10% reached their intended targets in London after the SCR-584 systems became operational on the southeastern coast. This defensive success meant that German resources devoted to V-1 production and operations achieved minimal results, a strategic failure compounded by tactical defeat. The Battle of the Bulge highlighted the SCR-584's capabilities in challenging conditions. During the initial phase of the German offensive, cloud cover extended from ground level to above 20,000 feet across most of the battle area. Conventional ground-controlled interception was nearly impossible. The SCR-584's ability to track friendly aircraft through clouds and guide them to targets identified by ground forces provided close air support capability that would otherwise have been unavailable. American forces used the SCR-584 systems to direct P-47 Thunderbolt fighter bombers to German armored columns moving through the Ardennes forests. The radar tracked the aircraft through the clouds, provided precise position information, and guided them to their attack runs. This capability helped contain the German breakthrough during the critical first days when Allied ground forces were reorganizing their defenses. The psychological impact on German troops of being attacked by aircraft they could not see was significant. The counter-battery capability that emerged from the SCR-584's precision tracking had implications beyond immediate tactical use. American artillery officers developed techniques for using the radar to track German artillery shells in flight, calculating the trajectory back to the firing position. This information enabled rapid counter-battery fire, reducing the effectiveness of German artillery and increasing the survivability of Allied forces within range of German guns. The system's ability to detect ground vehicles provided an additional intelligence capability. Radar operators could detect German armored formations at distances where visual observation was impossible. This early warning gave Allied commanders time to position forces and call in airstrikes before German attacks developed. The tactical flexibility this provided contributed to the Allied ability to respond rapidly to German initiatives. As the war in Europe approached its conclusion, the SCR-584 had become one of the most widely deployed radar systems in Allied service. The approximately 1,700 units produced were distributed across the European and Mediterranean theaters. They protected major ports, defended critical infrastructure, guarded forward airfields, and accompanied advancing ground forces. The system's reliability and effectiveness made it indispensable to Allied air defense. The legacy of the SCR-584 extended far beyond World War II. The system remained in service with various militaries worldwide into the 1950s. Its technical principles influenced radar development for decades. The emphasis on automatic tracking, microwave operation, and integrated fire control became standard features of subsequent anti-aircraft systems. The Soviet derivatives that emerged from stolen plans demonstrated the system's fundamental soundness by remaining operational through multiple conflicts. The post-war period saw the SCR-584 adapted for new purposes beyond its original air defense role. The system was modified for use in the AN/MPQ-12 and AN/MPM-38 field artillery missile systems. A modified version controlled and tracked the Corona spy satellites using onboard transponders. In 1953, the SCR-584 Mod 2 tracked Redstone rocket tests. Its range extended to 740 kilometers through use of onboard transceivers. The scientific community recognized the SCR-584's potential for research applications. The National Science Foundation's Center for Severe Weather Research adapted SCR-584 pedestals for mobile Doppler weather radars. These DOW systems created the first maps of tornado winds and discovered hurricane boundary layer rolls. The pedestal design's stability and precision made it ideal for weather research requiring rapid antenna positioning in high winds. The MIT Radiation Laboratory's work on the SCR-584 established foundations for Lincoln Laboratory, created in 1951 to develop air defense systems. The expertise gained developing the SCR-584 contributed directly to the SAGE air defense system that protected North America during the Cold War. The institutional knowledge and technical approaches pioneered with the SCR-584 influenced American radar development for generations. The human cost of the SCR-584's effectiveness is documented in Luftwaffe loss records. German air operations against Allied positions defended by the SCR-584 suffered casualty rates that made such missions nearly suicidal. Experienced crews were lost at rates that German training programs could not replace. The Luftwaffe's declining effectiveness in the final year of the war reflected many factors, but the loss of crews to SCR-584 directed anti-aircraft fire was significant. For the Allied soldiers protected by the SCR-584, the system's effectiveness translated directly into survival. Beachheads were secured, supply lines remained open, forward positions were shielded from air attack. The reduction in casualties from German air operations, while difficult to quantify precisely, was substantial. Every German aircraft destroyed by SCR-584 directed fire was an aircraft that could not strafe ground forces, bomb supply concentrations, or attack transport vessels. The production achievement, represented by the more than 2,000 SCR-584 systems manufactured, deserves recognition. American industry's ability to transition from prototype to mass production in 11 months, then produce complex radar systems at scale, demonstrated industrial capacity that Germany could not match. The General Electric Company, Westinghouse Electric and Manufacturing Company, and Chrysler Corporation established duplicate sources for all components, created specialized tooling, and implemented quality control procedures that ensured consistent performance across all units produced. The training infrastructure required to deploy over 2,000 radar systems was itself a substantial achievement. Training schools at Camp Davis in North Carolina and other locations processed thousands of operators and maintenance personnel. The curriculum covered radar theory, system operation, preventive maintenance, and tactical employment. The quality of this training ensured that systems reaching combat units were operated by crews capable of exploiting their full capabilities. The SCR-584's resistance to German jamming was not merely a technical feature but a strategic advantage. German electronic warfare doctrine, developed through years of experience, became obsolete overnight when confronted with microwave radar. The confidence German forces had placed in their jamming equipment proved misplaced. The realization that their countermeasures were ineffective required fundamental reconsideration of air operations doctrine. a reconsideration that came too late to affect the war's outcome. The technical sophistication of the SCR-584 reflected broader patterns in Allied weapons development. The integration of cutting-edge electronics, mechanical engineering, and tactical doctrine created weapon systems that were more than simple improvements over existing equipment. The SCR-584 represented a qualitative leap in capability that changed the fundamental nature of air defense. This pattern repeated across multiple weapons systems, from the proximity fuse to the atomic bomb, demonstrating the Allied commitment to technological superiority. The collaboration between British and American researchers that produced the SCR-584 exemplified effective international cooperation. The TISAD mission's decision to share the cavity magnetron with American researchers enabled developments that neither nation could have achieved alone. British theoretical advances, combined with American industrial capacity and engineering expertise, created weapon systems that changed the course of the war. This cooperation established patterns of technological sharing that continued throughout the war and beyond. The German failure to develop equivalent microwave radar capabilities reflected both technical limitations and strategic choices. German research into shorter wavelength radar existed but received lower priority than other projects. The decision to focus resources on existing systems that were known to work, rather than investing in unproven technologies, was defensible given Germany's strategic situation. However, this conservative approach meant that when Allied microwave systems appeared, Germany had no effective response. The individual stories of the German aircrews who encountered the SCR-584 are largely lost to history. Luftwaffe combat records from the final years of the war are incomplete, and many personnel who might have provided accounts did not survive. What remains is statistical evidence of declining effectiveness and rising casualties in air operations against Allied positions. Behind these statistics were men who faced increasingly desperate missions against defenses they could not overcome. The American radar operators who served the SCR-584 systems rarely received recognition for their contributions. Air defense successes are measured in negative statistics, in attacks that did not succeed, in casualties that did not occur. The dramatic nature of offensive operations overshadows the essential but less visible work of defensive systems. Yet the protection these crews provided was fundamental to Allied success in every major operation from Anzio forward. The SCR-584's story ultimately demonstrates the importance of technological innovation in modern warfare. The system emerged from fundamental research into microwave physics, enabled by British willingness to share critical technology, developed through American engineering expertise and industrial capacity, and deployed by trained operators who exploited its capabilities effectively. This combination of scientific knowledge, international cooperation, industrial production, and tactical proficiency created a weapon system that changed the nature of air defense. The Germans who encountered the SCR-584 at Anzio that night in February 1944 experienced a moment of technological surprise that foreshadowed the final year of the war. Their electronic countermeasures, developed through years of experience and refined through combat, proved useless. Their tactical doctrine, built on assumptions about Allied radar capabilities, required immediate revision. Their confidence in their ability to operate against Allied defenses was shattered by an enemy they could not see using technology they had not anticipated. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The lesson extends beyond World War II. Technological surprise remains a constant feature of military conflict. The side that achieves breakthrough capabilities, whether in radar, computers, or any other critical technology, gains advantages that purely quantitative measures cannot overcome. The Germans had more experience with radar, sophisticated systems, and competent operators. What they lacked was the critical technological edge provided by microwave operation and automatic tracking. The SCR-584 proved that innovation could trump experience, that quality could overcome quantity, and that technological superiority could change tactical equations fundamentally. The 7 German bombers destroyed at Anzio on February 24, 1944, were among the first casualties of this technological shift. Thousands more Luftwaffe aircraft would follow. The Germans never fully adapted to the challenge the SCR-584 represented. By the time they understood the magnitude of their technological disadvantage, the war's outcome was no longer in doubt. This is their documented story, verified through technical specifications, combat records, and historical analysis. The SCR-584 remains one of the most successful radar systems ever deployed, a testament to the scientists who designed it, the workers who built it, the soldiers who operated it, and the strategic vision that recognized microwave radar's potential. For the Germans who encountered it without warning, the SCR-584 represented a future of warfare they were unprepared to face. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.